Advanced glycation end product, Wikipedia audio. Advanced glycation end products are proteins or lipids that become glycated as a result of exposure to sugars. They can be a factor in aging and in the development or worsening of many degenerative diseases, such as diabetes, atherosclerosis, chronic kidney disease, and Alzheimer's disease. Ages affect nearly every type of cell and molecule in the body and are thought to be one factor in aging and some age-related chronic diseases. They are also believed to play a causative role in the vascular complications of diabetes mellitus. Under certain pathologic conditions, such as oxidative stress due to hyperglycemia in patients with diabetes, and hyperlipidemia, age formation can be increased beyond normal levels. Ages are now known to play a role as pro-inflammatory mediators in gestational diabetes as well. Effects. The animal and human evidence is that significant amounts of dietary advanced glycation end products are absorbed, and that DAEs contribute to the body's burden of age, and are associated with diseases such as atherosclerosis and kidney disease. In the context of cardiovascular disease, ages can induce cross-linking of collagen, which can cause vascular stiffening and entrapment of low-density lipoprotein particles in the artery walls. Ages can also cause glycation of LDL, which can promote its oxidation. Oxidized LDL is one of the major factors in the development of atherosclerosis. Finally, ages can bind to RAGE and cause oxidative stress as well as activation of inflammatory pathways in vascular endothelial cells. Increased vascular permeability, increased arterial stiffness, inhibition of vascular dilation by interfering with nitric oxide, oxidizing LDL, binding cells including macrophage, endothelial, and mesangial to induce the secretion of a variety of cytokines, enhanced oxidative stress. The formation and accumulation of advanced glycation end products has been implicated in the progression of age-related diseases. Ages have been implicated in Alzheimer's disease, cardiovascular disease, and stroke. The mechanism by which ages induce damage is through a process called cross-linking that causes intracellular damage and apoptosis. They form photosensitizers in the crystalline lens, which has implications for cataract development. Reduced muscle function is also associated with ages. Ages have a range of pathological effects, such as proteins are usually glycated through their lysine residues. In humans, histones in the cell nucleus are richest in lysine, and therefore form the glycated protein N-carboxymetallysine. A receptor nicknamed RAGE, from our acceptor for advanced glycation END products, is found on many cells, including endothelial cells, smooth muscle, cells of the immune system from tissues such as lung, liver, and kidney. This receptor, when binding ages, contributes to age and diabetes-related chronic inflammatory diseases such as atherosclerosis, asthma, arthritis, myocardial infarction, nephropathy, retinopathy, periodontitis, and neuropathy. The pathogenesis of this process hypothesized to activation of the nuclear factor kappa B following age binding. NF-kappa B controls several genes which are involved in inflammation. In clearance, or the rate at which a substance is removed or cleared from the body, it has been found that the cellular proteolysis of ages, the breakdown of proteins, produces age peptides and age-free adducts. These latter, after being released into the plasma, can be excreted in the urine. Nevertheless, the resistance of extracellular matrix proteins to proteolysis renders their advanced glycation end products less conducive to being eliminated. While the age-free adducts are released directly into the urine, age peptides are endocytosed by the epithelial cells of the proximal tubule and then degraded by the endolysosomal system to produce age amino acids. It is thought that these acids are then returned to the kidney's inside space, or lumen, for excretion. Age-free adducts are the major form through which ages are excreted in urine, with age peptides occurring to a lesser extent but accumulating in the plasma of patients with chronic kidney failure. Larger, extracellularly derived age proteins cannot pass through the basement membrane of the renal corpuscle and must first be degraded into age peptides and age-free adducts. Peripheral macrophage as well as liver sinusoidal endothelial cells and Kupffer cells have been implicated in this process, although the real-life involvement of the liver has been disputed. In other diseases, large age proteins unable to enter the Bowman's capsule are capable of binding to receptors on endothelial and mesangial cells and to the mesangial matrix. Activation of RAGE induces production of a variety of cytokines, including TNF-beta, which mediates an inhibition of metalloproteinase and increases production of mesangial matrix, leading to glomerulosclerosis and decreasing kidney function in patients with unusually high age levels. Although the only form suitable for urinary excretion, the breakdown products of age, that is, peptides and free adducts, are more aggressive than the age proteins from which they are derived, and they can perpetuate related pathology in diabetic patients, even after hyperglycemia has been brought under control. Some ages have an innate catalytic oxidative capacity, while activation of NADH oxidase through activation of RAGE and damage to mitochondrial proteins leading to mitochondrial dysfunction can also induce oxidative stress. A 2007 in vitro study found that ages could significantly increase expression of TGF-beta1, CTGF, FNmRNA in NRK49F cells through enhancement of oxidative stress, and suggested that inhibition of oxidative stress might underlie the effect of ginkgo biloba extract in diabetic nephropathy. The authors suggested that antioxidant therapy might help prevent the accumulation of ages and induced damage. In the end, effective clearance is necessary, and those suffering age increases because of kidney dysfunction might require a kidney transplant. In diabetics who have an increased production of an age, kidney damage reduces the subsequent urinary removal of ages, forming a positive feedback loop that increases the rate of damage. In a 1997 study, diabetic and healthy subjects were given a single meal of egg white, cooked with or without 100 grams of fructose. There was a greater than 200-fold increase in age immunoreactivity from the meal with fructose. Ages are the subject of ongoing research. There are 3 therapeutic approaches: preventing the formation of ages, breaking cross-links after they are formed, and preventing their negative effects. Compounds that have been found to inhibit age formation in the laboratory include vitamin C, benfotiamine, pyridoxamine, alpha-lipoic acid, taurine, pimagedine, aspirin, carnosine, metformin, pioglitazone, and pentoxifylline. Studies in rats and mice have found that natural phenols such as resveratrol and curcumin can prevent the negative effects of the ages. Pathology. Reactivity. Compounds that are thought to break some existing age cross-links include allogebrium and N-phenylethiozoleum bromide. One in vitro study shows that rosmarinic acid outperforms the age-breaking potential of Alt-711. clearance. Potential therapy. There is, however, no agent known that can break down the most common H, glucose pain, which appears 10 to 1,000 times more common in human tissue than any other cross-linking H. Some chemicals, on the other hand, like aminoguanidine, might limit the formation of H's by reacting with 3-deoxyglucosone.